So as we know, measuring pitcher skill is a complicated problem, and a big issue is that a pitcher's results depend on a lot of variables that are beyond his control. Things like the defense, ballpark, catcher, umpire, weather, just random luck. And there have been a number of statistics that start from results and then try and correct for these variables. Now what we're doing is taking the opposite approach. We start from the things that a pitcher can directly control, things like the speed, the movement, and the location, and we try to develop measures of skill just starting from those parameters. And there's a long history of associating values with individual pitches, going all the way back here to Pete Palmer, but if you go now to Fangraphs, you can get values for pitches for individual pitchers. But if you look at these pitch values, they have the issue, just like any statistic that's based on results, that they depend on all these variables that are beyond the pitcher's control, and therefore these statistics for these pitch values have a very low degree of repeatability. So what we do is we compute what we call intrinsic pitch values, and they start from only the physical parameters of the pitch, the speed, the movement, and the location, as well as the count and the platoon configuration, and compute the probability of all the different outcomes that can happen to that pitch as a function of those parameters. So the probability of a ball in play, a called ball, called strike, swinging strike, foul ball, hit by pitch, and we know the value of each of those different events, and now we know the probability, so we can put those into this intrinsic pitch value down here. And then for the balls in play, of course, those break down into all the different possible outcomes for balls in play as a function of the pitch parameters. So you hear talks where people talk about, for example, just looking at the balls in play or the exit velocity component, ignoring, Vince mentioned this morning, ignoring things like, well, there could be a called strike, a swinging strike. I've heard other talks where people just talk about the swinging strike rate and ignore the fact that maybe you have a good swinging strike rate, but the balls put in play are put in play with a lot of authority. So this combines all of these different possibilities for each pitch. And this is similar if you're familiar with the Woba cube. The Woba cube maps the batted ball parameters, the speed, and the spray angle and the launch angle into a value for batted balls. Same idea here based on the physical parameters of a pitch. The difference is we can't talk about something nice like a cube that you can visualize because we're operating in 7 dimensions. So all we can do is just take slices, lower dimensional slices, through that 7-dimensional space if you want to actually look at some of these results. So we'll show you a few of those. This is an example for a pitch that's typically classified a 4-seam fastball. So this is 0-0 count, right-on-right configuration. We've got the speed and the movement, and we're just looking at the location here, and this is from the catcher's perspective. And the pitcher wants low run values. These are basically run values for the pitch. So you see the best location for this particular pitch is down and away from the right-handed batter. And we can look at other configurations. This is a pitch that's typically classified as a changeup. This is an 0-1 count, right-handed pitcher, left-handed batter. And you see here that the pitcher really wants to avoid the middle of the zone, and the best location for this pitch is down and away, a little bit off the plate to the left-handed batter. And we can do other things like compute the exact value of an extra mile per hour on a fastball. So this is a plot where we're fixing everything except LX is the horizontal location of the pitch, and then we've got this pitch value as a function of that, and then the 4 different curves here are for different pitch speeds, and you see that as the velocity goes up, that the run value goes down, which is what you would expect, but we can quantify this very precisely. And you see that the biggest difference for velocity is pitches in here that are in the strike zone, the reason being that the batter is more likely to swing at pitches in the strike zone. Additional velocity doesn't help you if the batter doesn't swing. And same thing, this is same idea. We're plotting as a function of horizontal location. the dependence, the intrinsic pitch value dependence on, in this case, vertical movement, and you see as the pitcher gets additional vertical movement, we get lower run values for the pitch. And as before, where the batter's more likely to swing, the movement tends to help you more. We can look at things like, here we're plotting just the two movement components. We've got the horizontal movement and the vertical movement, and you can see that there's a band here for this particular pitch configuration that the pitcher really wants to avoid, and then you can look at the better values are up here and maybe even below that band that the pitcher wants to try and avoid. And this is the Cronback Reliability. So what that is, reliability was mentioned in the previous talk, but this is a way to compute the repeatability of a statistic. And what we're seeing here, we've got the intrinsic pitch values in black, that's this curve. This is as a function of the number of pitches in the configuration. So you see we're getting a fairly reasonable correlation just going out to say 100 pitches. And then the red curve is the observed pitch values. So this is what you see on fan graphs. And you see, as I mentioned before, there's a very low degree of repeatability because of all the factors, all the variables that influence what you can get for an observed pitch value. So almost down at 0, which would just mean you're measuring noise. So if you see a big value, which we see here, that means that you're measuring some kind of a persistent skill. And we can look at this. This is for another configuration, same result. If you go to the paper, you'll see lots of curves like this, but they're all telling the same story, that we're getting a very nice reliability for these intrinsic pitch statistics. Okay, so we can take these measurements for individual pitches, and then we can sum them up into a value, say over a season or over whatever time period you want, by doing a weighting for the count. If we do that for the observed pitch values, what you end up with is just the WOBA that the pitcher allowed over the course of that period of time. And that, of course, depends on all these variables that are beyond the pitcher's control. But if we do this with the intrinsic pitch values, then it only, again, depends on velocity, movement, location of the pitches, just the physical property. We can sum those up. And what we find is that, for example, if a pitcher overperforms his intrinsic values during a season, he tends to do worse the following year, and we get more predictive value for, say, earned run average for next year than you get out of things like fielding independent pitching or current year ERA. So it's both reliable as far as measuring a persistent skill, and it's more predictive than other measures if we're trying to look at what the performance will be next year, which is what you might expect since we're going just to the physical properties of the pitch. Another thing we get here that I can kind of mention, since we know the probability of each event, we can also re-weight the number of times a pitcher gets to each count. So if you think of a pitcher that's always throwing to a good framer, he might tend to get into better counts more often than he deserves. But here we can also factor that out directly because we know all of these probabilities. Okay, now another advantage of starting with parameters that the pitcher has direct control over is that we can try and use these for pitch design, pitch development. So if we know the value of movement on a pitch, we can say, okay, how can this pitcher try to take the talent that he has and try and optimize to get into the ranges that are going to give him the best performance. So we can do that by further breaking down, in this case we're going to break down the components of motion into parameters that the pitcher has even more direct control over. And we're going to be able to do that because TrackMan gives us not just the trajectory parameters I've mentioned, but also the total spin on each pitch. So if we have a ball flying through the air with a velocity vector v, there's three forces on the ball. There's gravity pulls it down. There's drag that operates opposite the velocity direction. And then there's the Magnus force that can change the direction of the ball due to spin. And we'll be talking a lot about spin here. So it's important to recognize that spin is a vector, has both a magnitude and a direction. The magnitude of the spin is just how fast the ball is spinning. That's what TrackMan measures, maybe 2,400 RPM. And then the direction of the spin is defined by the axis that the ball is spinning about. And the pitcher controls the spin axis with the orientation of his hand and fingers when he releases a pitch. Now, I've written down some equations for people who like equations, but even if you don't like equations, the important thing here is that the amount of spin that gets transferred to the Magnus force into movement on a pitch depends on the relative directions of the spin axis, that's this omega, and the velocity direction v. So we've got the omega hat and the v hat are unit vectors in those directions, and if those two vectors are perpendicular, then it turns out that all of the spin gets transferred to movement on a pitch. So we might say all of the spin is useful, and I've been having conversations with Alan Nathan and Tom Tanga recently, and we're thinking that maybe active is a better word than useful, so I'll probably use those interchangeably here, but we'll have to decide on what we want to call this. The other extreme is if the omega and v vectors are parallel, then none of the spin gets transferred into movement. So if we look at a couple pictures, the top picture is a fastball that only has backspin. So in this case, you can see the velocity direction and the spin vector are perpendicular. So all of the spin gets transferred into Magnus force. Magnus force direction is straight up. That would be a rising fastball. The other extreme is a gyro ball, or might also be called a backup slider or a cement mixer. And here you can see that the velocity direction is parallel to the spin axis, so none of the spin gets transferred into movement. So the Magnus force is 0. And let's look at some real pitches. Okay, most pitches don't have either perpendicular or parallel. They're somewhere in between. So here we've got some data from a game, Yankee Stadium, Red Sox, Yankees in 2017. And these are all of the four-seam fastballs that Kimbrel and Betanzas threw in that particular game. And we've got Betanzas in blue and Kimbrel is in red. And we've got the spin rate and the speed. And what you can see is that you really can't distinguish the Kimbrel or Betanzas four-seam from the spin rate and the speed. They look pretty much the same. But it turns out that Kimbrel got a lot more swings and misses on his four-seam, and he got a lot weaker contact when the batters put it into play. So you can ask, well, why is that? It's not the speed, it's not the spin rate. What it is the spin axis. So here we've got those same pitches, again, Kimbrel in red, and we're looking at the movement, horizontal and vertical movement on the pitch, and you see that Kimbrel has much more movement. Red pitches are pretty much all to the right of the blue pitches, and it's mostly in the horizontal direction, and that's because of the spin axis that Kimbrel uses when he throws this particular pitch. Okay, so given that this spin axis is important, we went through the exercise of trying to compute this for all of the pitches over the course of a season, and we're using a technique that Alan Nathan wrote up a few years ago, and I'll briefly outline how this works, but we get a trajectory model from TrackMan, and that allows us to separate out the contributions of the different forces. In particular, gravity's known, but we can also separate out the drag and the Magnus force. We also need the air density for each pitch, and what we did, one of the reasons we had so many students involved in this project, is we found the air density, starting with the weather conditions, for every pitch thrown over the course of a full season at the granularity of trying to get within 10 or 15 minutes of each pitch at a nearby weather station near the ballpark. So we've got the weather data, we've got the altitude, and the math that we're using to compute the air density is described in the reference there at the bottom. And just an example of the effects of air density on movement, this is German Marquez, his four-seam fastballs in 2017, and we're plotting the actual measured vertical movement on the pitch as a function of air density. And you can see there's a lot of scatter in the movement, and we'll come back to that, but that's fairly well known. But you see that there's an upward trend, as if you were paying attention to an equation a few slides ago, we saw that the magnitude of the Magnus force goes up with the air density. And you see that it is a fairly strong effect. Low air densities, you might think of a warm day in Colorado. High air densities, you might think of something like a cold night in Boston. So once we have the air density, we can compute what's called the lift coefficient and the spin parameter. Spin parameter is also just a scalar times what's called Bauer units. And the lift coefficient is known to be an increasing function of the spin parameter times this fraction of active spin, this magnitude of the cross product omega hat with v hat. That's the fraction of active spin. And this function is important because it tells us for a given set of pitch parameters how much movement, how much lift the pitcher is getting for that particular pitch. And people typically estimate this function with video analysis because from video you can get both the pitch trajectory and the spin axis. But from TrackMan we can't directly get the spin axis, but we wanted to see if we could try and find it and then use it to try and get this function out. Because with TrackMan we've got hundreds of thousands of pitches to look at. Video data typically looks at a much smaller number. But the issue again is we don't know this fraction of active spin directly from the TrackMan. So what we could start with is we said, well, fastballs are known to typically have mostly useful spin or mostly active spin. So we could just take all the fastballs and see if that gives us a nice curve, just plot CL versus S. We do that for the whole year 2017, hoping to get a nice curve, and we don't get a nice curve, we get a big blob. If we fit a line to the big blob, it has the increasing trend that we were hoping for, but there's no chance you're going to get a curve out of something that looks like that. And if we consider what's causing this to be a blob instead of a curve, well, there's a number of sources of scatter. There's ballpark bias. There's, even within fastballs, there's variation in the useful spin fraction, this magnitude cross product. There's also random measurement error. So just some examples. This is 2017, and we just have a scatter plot of horizontal and vertical movement. Jacob deGrom, four-seam fastball, and you can see that he's getting credit for a lot more horizontal movement on average at home than he is on the road. Another example, this is Irvine Santana, 2017 four-seam, same scatter plot of movement. You see here that he's getting credit for a lot more vertical movement in his games at home than he is on the road. And overall, we identified 7 ballparks in 2017 that seemed to have significant issues with the movement parameters. So we're working on 2018 now. We'll see how that looks, but just something to be aware of. Another source of scatter is just random variation, random measurement noise. So here we're taking a single pitcher, Justin Verlander, single pitch, four-seam fastball, plotting CL versus S, and you see that we get a smaller blob than we had for all the pitchers, but we still get a blob. We ran what's called an OKG covariance analysis, and that allowed us to throw out the red points. Those are the most severe outliers. And then we compute a robust mean from just the core of the distribution. So doing this, we can take an individual pitch type from an individual pitcher and boil that down to a single point of CL versus S. And here's the result of doing that. So each point on this plot is a pitcher, and either the blue points are four-seam fastballs, the red points are two-seam fastballs. And you see that we still don't get a nice curve. There's still a lot of variation in the vertical direction, but that is due to the fact that different pitchers, even with the fastball, have a significantly different amount of active spin. So you might remember that the lift coefficient is a function of S, the spin parameter, times the active spin fraction. So the points we want, if we want this function, are the points that bound the top of the distribution. And you see that we get a nice line here, this green line here, to fit the top. And the guys at the top are Garrett Cole, Miguel Gonzalez, and Marco Estrada. And the model that had come out of the video analysis is this black curve here. It's a little bit lower, so we're seeing more lift for a given value of S. So if you want to start a conspiracy theory, you could say the ball has changed, and that's what's giving pitchers more movement according to these functions. I don't know about that, but that's what we're seeing here. And then some other points, you can see that and we'll talk more about this later, the active spin fraction is about the same between 2-seam and 4-seam. And another point is that once we have this green curve, if we're seeing points at a ballpark that are consistently above that green curve, that indicates some kind of calibration issue, something that MLB might be able to use to try and make things better. So once we have that function, then we've got everything we need to compute the spin vector, and the formula is here. It's just an additive combination. This is the active spin, and then this is the gyro spin that we can get because we have the total spin measurement from TrackMan. The plus is the gyro spin component if you're right-handed, negative if you're left-handed. And as I'd mentioned, there's a bit too much scatter in individual pitches in the measured movement, so we can't really compute this very reliably for a single pitch. But if we're looking at a pitcher and a pitch type over a period of time, then we can do a reasonable job. But we still have to be careful. This is an example. It's a histogram of the useful spin magnitude for Zach Greinke, 4 seams, 2017. And one of the things you notice is that we've got a heavier tail going out to the right, which is just an artifact of the measurement process. If you compute the mean is more than 100 RPM bigger than the median. So you want to use robust estimates again, and we use estimates based on the median for all of these things. With this, we create what we call a spin diagram, and what this does is for a pitcher and a pitch type, we represent the direction of a pitch as the direction of the Magnus force from the pitcher point of view. That's the direction the pitch is moving. And then the length from the center is equal to the useful spin fraction. So if a guy has 100% useful or active spin on a pitch, then it'll lie on the boundary of the circle. And here we've got the Kimbrel and Betanzas 4-seam that we talked about earlier. You can see that Kimbrel has a higher spin efficiency, about 80% to about 71% for Betanzas, and also that, as we saw before, the force is more in the horizontal direction for Kimbrel. We can compare pitchers with themselves. This is Verlander with the Tigers, and then Verlander with the Astros in 2017, 4-seam. You can see that he made an adjustment on the pitch. He went from about 90% efficiency to about 98% efficiency by making a fairly small adjustment. And of course, if you remember, that led to much better results. These are the averages by pitch type over 2017. Right-handers in black, and then the left-handers are mirror image in the red. And the pitches with the most upward force are the 4-seam, most downward force are the curveballs, and the fastballs and the changeup have the highest efficiency. And then something else we've done is we've looked at spin signatures and how they compare across pitchers. We used, I've talked before about the earth mover's distance, so we used that here to find the most unique spin signatures in 2017. You can see the pitchers here, and we'll just show you a couple of these. This is Charlie Morton, and we've got his pitches in red, and then the league average for the same pitches are in black. You see he has a lower than average arm slot because these pitches rotate down. You see he's got a much higher spin efficiency than league average on his fastball, and also a more efficient curveball. This is Aaron Nola. You see he also has a lower than average arm slot by the rotation of his pitches. His changeup in particular has a much larger downward force on it. He gets many more ground balls than the average pitcher on the changeup. And you can also see that he's got a lot more efficient curveball here, so a lot more glove side movement on the curve. And then a couple left-handers. Brad Hand, the thing that stands out is just this ridiculous slider over here, which if you've seen him pitch, you can appreciate. Alex Claudio, the big thing here is he throws almost sidearm, so the pitches are rotated way down. He gets a ton more ground balls than is typical. Okay, so in summary, we have implemented Allen's method for computing spin axis. That led to a new model for lift force. And we have some pitch descriptors that I've described based on pitch physical properties, invariant to defense, ballpark, catcher, umpire, weather. And we've shown that these have a higher reliability and predictive value than other measures. And there's a lot of applications. We've listed some here. Pitcher development, pitch design. We can compare pitchers across time and competition level very easily because we're just looking at the physical parameters of a pitch. We can optimize projections for performance, aging, health, model environmental factors, weather, altitude, and also help with the automated generation of matchup models. So that's all I've got. I can answer questions if we have time. Yes, Alan.
How do you handle the ballpark bias when getting the lift formation?
At this point, we just throw out. We've identified the bad ballparks and we throw them out. Pitches thrown there. Yeah, otherwise you get a whole bunch of points up above the green curve and you say, this guy can't be that good. And,
do you have any ideas about how to handle it in the future?
Well, I think we could just try and correct it. If we can identify it, I think we can develop methods looking at home and away to try and bring it back so everybody's about the same. Yeah. Any other questions? All right.